Hey, Math 206 students. Today, this corresponds to Tuesday's lecture. There's an exam coming up on Friday. And so what I'm about to talk about, or what I will talk about today, is the last of the material that you'll need to know for the exam. So last time we were talking about the column space and the null space. There's also the row space. I really don't emphasize the row space. It's not that important, but it does show up in the book, or I shouldn't say it's not important. But let me just define it. So the row space of a matrix you can think of as the column space of A transpose. So let's see, the column space of a matrix is the span of the columns. The true definition, or maybe the way you want to think of it, the row space is the span of the rows. I like to think of them, though, as column vectors. So if you take the transpose, all the rows become columns, and so the row space you can then think of as the span of the columns of A transpose. And here's a fact. Well, here's a fact. The dimension of the column space of A is exactly equal to the dimension of the row space of A. Right? And in just shortly, I will actually write this down, or I'll need this for a theorem that we state a little later. So anyways, there's the row space. I really don't emphasize it. I'll make a big thing out of it. When you read it in the book, though, you want to know what it means. And so the row space is just the span of the rows of the matrix. Think of it in terms of column vectors as the span of the columns of A transpose. Okay, so now, so let's let A be an M by N matrix. The rank of A is, and we'll write that as rank parentheses A. By definition, it is the dimension of the column space of A. So the rank is the dimension of the column space. There's also the nullity. So the nullity of A is, and we write this as nullity of A, and it's the obvious thing, it's the dimension of the null space of A. Now, a minute ago, I said that the dimension of the column space is equal to the dimension of the row space. So you could say note rank of A is equal to the dimension of the row space of A. Now, here's something to pay attention to. So let's notice this. If we look, we've got this M by N matrix, and if we look at it, N is equal to the number of leading variables plus the number of free variables in the homogeneous system, right? I mean, you're either a free variable or you're a leading variable. The number of leading variables is exactly equal to the rank of A, right? That's the dimension of the column space, the number of pivot columns. And then if you're not a free variable, if you're not a leading variable, then you're a free variable, and the number of free variables corresponds exactly to the number of basis vectors in a basis for the null space. And so the free variables, this is exactly equal to the nullity of A. So combining this, or putting all of this into a theorem, and this has a name, it's called the dimension theorem. And it goes like this. So if capital A is an M by N matrix, then N is equal to the rank of A plus the nullity of A. Right, so I mean, this is an important theorem, but it's really not difficult, right? I mean, you're either a leading variable or a free variable. Combine those two together, that tells us how many columns our matrix has to have. So as an example, let's say that we've got A equal to the following matrix. I'm going to go row by row, 1, 0, 1, 2, 3. 1, 0, 1, 2, 3. 0, 1, 2, 3, 1. 0, 1, 2, 3, 1. And 0, 1, 2, 4, 0. 0, whoop, 0, 1, 2, 4, 0. Okay, I would like to just identify the rank and the nullity of this matrix right here. We've got a 3 by 5 matrix. If you get it in row echelon form, it'll look like this. Oh, I guess did I put it in reduced? I just put it in row echelon form. So 1, 0, 1, 2, 3. 0, 1, 2, 3, 4. And 0, 0, 0, 1, minus 1. 0, 0, 0, 1, minus 1. Okay, so that's in row echelon form. Here's what we get. There are 3 leading ones. That would tell us that a basis for the column space consists of columns 1, 2, and 4 of our original matrix. And so what does that tell us then? The rank of A equals 3, and the nullity of A equals 2. Now, there's some consequences to the dimension theorem. So consequences of the dimension theorem are, and these consequences are, we're going to add a bunch more parts to the equivalence theorem. So we'll say additions to the equivalence theorem. So remember, that's the theorem that has a bunch of things that are equivalent to our matrix A being invertible. And so if you're keeping track of them or keeping a list, hopefully you kept some space there. So remember, it goes like this. I'm writing the start or the beginning of the equivalence theorem. If A is n by n, the following are equivalent. That's an abbreviation for the following are equivalent. Part A, remember, is A is invertible. The last one we had was when we were talking about determinants. That was part G, is where we left off, and that was that the determinant of A is non-zero. So now we're going to add parts, these are going to be parts H through O. So we're going to be adding 8 new parts to the equivalence theorem. And my feeling on the equivalence theorem, I don't really memorize, in fact, I don't memorize all the parts of the equivalence theorem, but I understand why each one of these is true, and so when I need to use a certain fact about, these corresponding equivalents to being invertible, right, I'm able to use them, but I really don't have them memorized. So part H, the columns of A are linearly independent. Part I, and this is why I mentioned the row space, but so it turns out, right, that, right, because the dimension of the row space is equal to the rank, the row space of A, or the rows of A, the rows of A are linearly independent. Part J, the columns of capital A span Rn. Same statement, but replace columns with rows, so Hij, the rows of A span Rn. Hij, the columns of A form a basis for Rn. Same thing, Lm for rows, so the rows of A form a basis for Rn. You should understand why all of these mean the same thing, especially thinking in terms of, just focus on the column statements, right? So what do we know last time? If you have n linearly independent vectors in Rn, you're guaranteed that it forms a basis. So span and linearly independent go hand in hand with forming a basis when we're working with an n by n matrix. Two more parts, Lmn. So part n, the rank of A, well, let's see, if the columns form a basis, the rank of A has to equal n. And then part O is that the nullity of A then will have to be equal to 0, right? If the set of columns are independent, right, then there are no free variables. Okay, so that finishes off, or doesn't finish. We will add some more parts to the equivalence theorem, but these are the consequences that we get from the dimension theorem. So, as an example, let's show that the following set, call it capital S, consisting of the following vectors: 1, 1, 1, 0, 1, minus 1, and 1, 1, 0. I want to show that this set is a basis for R3. Okay. So let's see, how do we go about that? Well, there's lots of different ways, but if we notice that forming a basis, if the columns of a matrix form a basis for Rn, that's the same as being invertible, and we know a way to check for invertibility. That's with the determinant. So one way to show that this set of three vectors right here forms a basis is to compute the determinant of the matrix whose columns are exactly the ones that we see here. If I get non-zero, then I'm guaranteed that these vectors right here form a basis for Rn. So let's see, the determinant is going to be 1 times 1 plus 1 times -1, -2. So we get -1, which is non-zero, and then we can apply the equivalence theorem. The determinant is not equal to 0 is equivalent to the columns of A forming a basis for Rn. Right? So a determinant allows us to identify a basis. Yeah, okay, let's call this a definition, I guess. So let's let W be a subspace of Rn. The set, which we write as W with a little perpendicular symbol right there. So, and I usually will call this W perp. The set W perp consisting of all vectors orthogonal to all vectors in W is it's called the orthogonal complement of W. All right, so start off with this subspace, identify all vectors in Rn that are orthogonal to every single vector in W. Right? That set has a name. It's called the orthogonal complement. Now, remember when we say the word orthogonal, that's the same as saying that the dot product is equal to 0. And so notice that if, let's say, little w is in capital W, and how about u and v are in W perp, then the first thing to notice, if we do 0 dot little w, that's equal to 0, right? 0 vector dotted with any vector is equal to the number 0. So 0 is in W perp. Also, if we look at u plus v dotted with w, dot product satisfies the distributive property, so that's u dot w plus v dot w. That's 0 plus 0, which is 0. And if we do, say, constant times u dot with w, that's equal to r times u dot w. There's another property of dot products. You can slide constants out. Kind of like an associative property, although not quite. U dot w, because u is in the orthogonal complement, that's equal to 0. So we get r times 0, which is 0. So what did I just show? I showed W perp is guaranteed to be non-empty. The sum of two vectors that lie in W perp is also a W perp. Same with scalar multiplication. So, conclusion, W perp is a subspace of Rn. Right, so every time you have a subspace, there's another subspace. That's the orthogonal complement. A couple of facts about the orthogonal complement. First, hopefully you've seen this symbol before. This is the intersection, so it's the set of all things that are in common to both W and W perp. So the intersection of W with its orthogonal complement, the zero vector alone. So they have very little overlap. The only place that these two subspaces interact or overlap is at the zero vector, at the origin. What else? Oh, also, the orthogonal complement of the orthogonal complement is the space itself. Now, let's say observe that if A is invertible, and let's say W equals the column space of A, then what does that tell us about W perp? Well, if A is invertible, then the column space of A is equal to Rn, so W is equal to Rn, so that means there's nothing left for W perp to be except the zero vector. And also, if V equals the null space of A, then, well, let's see, if A is invertible, then the null space consists of just the zero vector, only the trivial solution. So that means that V perp is equal to all of Rn. And so, to finish off today's lecture, we have two more parts to add to the equivalence theorem. And so these are going to be P and Q. P, the orthogonal complement of the null space of A is equal to Rn, and part Q, the orthogonal complement of the column space of A is trivial. It's just the zero vector. Okay, so that's a good place to stop. We are done with new material. We won't have any new material until after the next exam. So remember, today is Tuesday. We will review on Thursday. Exam is on Friday. Okay, so we'll see you then.